Okay, so dear students, so next problem is about the it's a heat transfer problem where heat is actually being okay, this heat has been dissipated to the atmosphere, okay, from a pin fin. So what is pin fin is, so here all of you have seen a fin, right? Fins, fin, fins are used to, I can say, to release the heat from a heated object, they release the heat to the atmosphere. So in engines, in bike engines, you have seen fins, right? These are the fins. So here a pin fin, here we have something from where heat is being generated, and from here we have a circular structure like this. So here heat will be, obviously this is the conductor, so heat will be conducted to this, and your air will be flowing over this, so heat will be dissipated to the air, okay, like from this part. So this is called pin fin. So this is a kind of pin, okay. So from the pin fin heat is being radiated. So we know it's we have just taken an let's say this is a ordinary differential equation. So the differential equation for the heat transfer is this, okay, k d square t by dx square equal to ph divided by ac into t minus t infinity, okay. So and the let's see this the terms here are, you see, k is coefficient of thermal conductivity, okay, the unit is watt per meter per degree centigrade. So perimeter, p is a perimeter, that means this entire perimeter from here to here, the circumference, okay, or the perimeter. If the radius is known, perimeter is 2 pi r, okay. Then we have cross sectional area of this. So this is circular, so the diameter is given, so cross sectional area can be found. H is convective heat transfer coefficient, so convection is present, so there is convective heat transfer coefficient is present, okay. Conduction is also there, so that's why coefficient of thermal conductivity is also there. Conduction through from this wall to this pin is there. Convection, convection both are present. So next, wall temperature. Here wall temperature where the source temperature is given Tw, and T infinity is the ambient temperature. T, it is not alpha, this is infinity, okay. T infinity is ambient temperature, the outside temperature, okay. The values of coefficient of thermal conductivity is given, convection heat transfer coefficient is given, and your outside temperature, that is the ambient temperature, is also given, okay. So what you have to do is estimate the temperature distribution in the fin using Galerkin weighted residual method. So that expression, that equation is given, two boundary conditions are given. So at x equal to 0, so here x here is sorry, the very, yeah, x will be, actually this is a unidirectional problem, so this is x, okay, x is not shown here, so x will be here in this direction, okay, x this direction. So at x equal to 0, so here this is the wall, okay, at x equal to 0 is wall because starting point is wall, okay, and x equal to L is the ending point of pin fin, okay. So at the starting point we know its temperature, that is at x equal to 0, that is the T wall only, that is 200 degrees centigrade at the wall, okay. And the dt by dx, this is the flux, sorry, this is your you can say temperature gradient, dt by dx at x equal to L is equal to 0 at insulated tip, okay. And that means this tip is insulated, okay, and there is a gradient, the temperature is not change, will not change with respect to x here, okay. So next is, some more informations are given. This is in the question itself. So 2 mm diameter of this pin is 2 millimeter, 30 mm long aluminum pin fin. So as shown in figure, used to enhance heat transfer from surface wall maintained at 200 degrees centigrade. So the entire, you can say, informations are given. So this wall is at 200 degrees centigrade. The pin fin is used to, I can say, dissipate heat to the atmosphere. So wall is at 200 degrees centigrade and atmosphere is at 20 degrees centigrade, okay. So that your governing expression is also given, as governing equation is given, and you have to find out your you can say temperature distribution, that means T. Okay, T at, I mean, find an expression for T in terms of X. Okay, so that means you can find out the temperature at any point, any given point. Let's say at this point we want to find. Okay, we can find once we solve it, once we solve and get T from this expression. Okay, so the problem is similar to the previous problem that we have explained here. Okay, now let's look at the solution. So the differential equation is this one. Okay, fine. So we are given with the value of K, this perimeter we can calculate. This is your H is given, this is your conductivity heat transfer coefficient, S is the cross sectional area, and this T is what we have to find out. Okay, this T and this T both are actually the these are the secondary variables or dependent variables which are dependent upon X. Okay, and T infinity is given to us. So 200 is the value given for K. Okay, here 200 watt per meter per degree centigrade, H is 35 watt per meter square into degree centigrade, and T infinity is 20 degree centigrade. So since all are in degree centigrade, so we are say the consistency of unit is there. So K is 200, we will directly put. So this is perimeter is 2 pi r multiplied by H is 35, S is pi r square, that is your cross sectional area, T minus 20. Thus by solving this, you see r gets 2 pi gets cancelled out, and radius here is given in, I say diameter is 2 millimeter. Okay, or radius should have been 1 millimeter here. Actually I made a mistake here. Okay, so since I have already I did the calculation. Okay, so just take this as 1 millimeter. Sorry, this will be, radius will be half of that, so this is 4 millimeter. Okay, so this is the correction. So yeah, so just note it, please note down that this problem, the diameter is 4 millimeter. Okay, and here what you have to do is, here the radius is 2, that is half of that, that is 2 into 10 to the power 3. Okay, so this I mean radius gets cancelled, also r is here. All right, so here d square T by dx square. So after solving all this, what we get, this is the simplified expression, right? And you know this now after simplifying, I mean see, this is the same expression after putting the values, right? So here what you have to you just use the make use of your make use of your boundary conditions. So boundary conditions, that is at T that x equal to 0, this is 200, and dt by dx is at x equal to L is 0. Okay, now I mean we are going to use that later on. Okay, now just assume, now see d square T by dx square is there, right? So we can just see, actually for this problem we can take a trial function starting with this. So T is equal to T of x is equal to c0 plus c1x plus c2x square. Okay, starting with this, we can also take it as c0 plus c1x plus c2x square plus c3x cube. Okay, we can also try with c0 c1x plus c2x square plus c3x cube plus c4x to the 4. The higher order, I mean the higher the terms you take, the more will be the calculation, because your weighting function will be, okay, there will be more weighting functions and you have to solve for all of them, but your calculation will improve. Okay, your approximate and solution will be improved. So here what you actually at least you take up to this. Okay, so this, for this problem I have taken up to this, but you can take higher order terms also. Okay, so you can try with that and you see what you get. Okay, so now all right, so here you see T is this one, so dt by dx is c0 c1 plus 2 c2x. Okay, then using the boundary condition, so at x equal to 0, that is 200, so c0 plus c1 into 0 plus c2 into 0 square, so c0 is 200. Okay, so dt by dx at x equal to L is equal to, now see this is c1 plus 2 c2x, so c1 plus 2 c2 into x at in place of x we put L, equal to 0. So C1 is equal to minus of 2C2L. Okay. Now therefore the solution is, in this case, now see C1 here is minus 2C2L, so put that, and C0 is 200. So here you see C0 is 200, so put that C0 is 200 here. C0 you have found as 200, so this is 200. Okay, plus in place of C1 we put minus of 2C2L into X, and C2 is there. So C2 multiplied by this expression is we have got. So this is your you can say trial function. So C2 multiplied by this we can take it as weighting function here. Okay, C2 multiplied by this weighting function. We can actually, we normally take it like that. So constants multiplied by whatever function that we have, that we take it as weighting functions, W. Okay, so the residual form for the equation is, yes, for this expression, this is the expression, right? So we just make this right hand side as 0. So d square t by dx square minus 175 into t minus 20 is equal to 0. That will be, I mean, the left hand side is your residual. So residual form is, okay, this is the residual, right? Just by taking whatever we had in the right hand side, take it in the left hand side. So this is your residual form. Okay, next is yeah, so residual form was d square t by dx square minus t 175 t minus 20. Okay, just put this what you have to do is, you have to actually differentiate. T is equal to C0 C1x plus C2x. So t by dx is equal to C1 plus 2C2x, and d square t by dx square is equal to 2C2, right? So after differentiating it twice, we get 2C2. So minus 175 into t minus 20. So 2C2 minus 175. So t here, this expression here that we have just got, okay, this one 200 plus, okay, C2 multiplied by x square minus 2l square lx that we put here, okay, minus 20. Now this is the your residual, okay, complete residual. Now I have to minimize the residual. For what value of C2, this entire residual becomes 0. Okay, that is what we need at each and every point. That means at each and every point of this fin, okay, the residual has to be minimized. The residual has to be 0. If it is 0 everywhere, then your exact solution you have obtained. If it is not 0, then it is not exact. Okay, so this is approximate. All right, so it has to be exactly 0, and if there is very small values are there, then that there are error. Okay, error are there. Okay, we'll look into that. Okay, so yes, obviously these are numerical methods, so errors are present, but we have to minimize the error. Okay, so to minimize, what you have to do, you have to multiply. We have to multiply a weighting function wx multiplied by the residual, integrate it over the domain equal to 0. Okay, so weighting function we have to choose as same as the trial function. Okay, here you see you have to actually take the weighting function as, these are actually piecewise, you can say, weighting functions. So this is one part, okay, and the expression which contains x, okay, and multiplied with your constant, that is taken as your weighting function. So here your weighting function, there is only one, so we have taken, we can write it as w1 also, or simply w, that is in terms of x, that is x square minus 2xl, and multiply this w into r into that is dx integration of 0 to l equal to 0, set it equal to 0. So here x square minus 2lx is there, so put this whole expression, entire expression of rd here. Okay, then you solve it. Okay, just by solving this, we have multiplied everything, we have simplified it, and then we have got this expression completely. C2 has been taken common, and then after integrating each and every time term, we get 175 by l to the power 5. I have just directly put l here, minus 0 will be there, so all the expressions, and after putting l there, so we have here like this. So l cube and l to the power 5 is there, l cube gets cancelled out, l5 becomes l square, So we get an expression like this. So C2 is equal to 21,000 divided by 93.33 L square plus 1.33. So this is the constant we have obtained by minimizing the residual. So this expression, this value of C2 will minimize the residual for the entire domain. Okay. Now therefore diagonal trial solution. So once we get the constant, we have to put it there. So 200 plus C2 into x square minus twice 2lx was there. So C2 value is this 21,000 divided by 93.33 L square plus 1.33. Now we were given with the length 30 millimeter as the length of your pin fin. So this is nothing but 13 to the minus 3 meter. So T of x is equal to 200 plus 21,000 divided by 93.33 into 30 minus 10 to the power 3 whole square plus 1.33. The whole expression is being multiplied with this. So 200 plus. So by putting the value of L, we get this as the expression. Now for at any let's say for we want to find out the temperature for the pin fin at the middle. So this is x is equal to L by 2. So we have to put L by 2 here. Okay, L by 2. This is L by 2. So L square, this will be L square also. So like L by 2, this will be L square only. This will be L square by 4 something, and then you get the value here. Okay, so L has to be known there. Okay, so this explanation is the required approximate solution using weighted residual technique. So we have seen two you can say examples of application of weighted residual technique. Okay, FEM actually has many things to learn. These are the preliminary examples of finite element method. FEM is very it's a fast subject. Okay, it's a very useful numerical technique. Okay, and FEM has more developments. Like this is, we are talking about only one dimensional problem, so we can solve 2D 3D all these problems, the partial differential equations, okay, which are very complex, right? So we can make mathematical models from there, all these. Okay, and there are actually FEM formulation for you can say each and every element, and elements are there. Okay, suppose it is a 1D line element. Okay, so 2D element is there. Okay, like any element like this. Okay, 3D element is there. Okay, 3D element, brick element is a 3D element. Okay, all these elements for the elemental equation can be obtained for using FEM. Okay, and then the entire problem is solved for each and every element, and finally they are assembled to get the complete equation, as I have explained in the first lecture of your FEM. Okay, so softwares like ANSYS, okay, then Abacus, okay, and Hypermesh, all are there. They use the technique FEM technique to solve your problems. Okay, they are actually approximate solutions, that's why they are numerical solutions, that's why they are approximate, but they will give you a pretty good result. Okay, and you know that CFD, computational fluid dynamics problems, they are actually solved by using generally that techniques we have learned in your finite difference method. Okay, that we have learned previously before this module. Okay, so your this numerical method subject was for your it was aimed to give you the basic knowledge about the numerical techniques we follow. There are more numerical techniques, we have covered some of them, but there are other techniques also present. Okay, so you can go through all these yourself, and yeah, so about FEM, this is not the end. Okay, so we have more can say many more in FEM finite element method, but this is just an introduction for Galerkin weighted residual. There are other weighted residual methods also. Okay, collocation method and many methods are there. Okay, so you can go through all the methods and you can learn them. That will be useful for you. Okay, thank you.